Okay, so once again, we're going to solve a initial value problem. Okay, this is our differential equation, and we have two initial values. Let me ask you, is this what's called a boundary value problem? Is this a boundary value problem? They're calling it an initial value problem. It's not a boundary value problem. Why is that? Well, you have what for about you have one initial condition on y, the other initial condition is on y prime. A boundary value problem. So you know we need two initial conditions, right? But a boundary value problem would not have a condition on the derivative. It would have like y of 0 equals 2,
Just two conditions
and y
on
of
the initial
1
function.
equals
Yeah.
4 or something like that. Okay, you wouldn't have an initial condition on the derivative. Okay, so I guess I'm glad I asked that question. Okay, so what we got to do, let's move forward here. All right, what we got to do is, okay, we let y equal the power series, n equals 0 to infinity of c sub n xn. Y prime is going to then equal the power series starting at n equals 1 to infinity of n times c n times x to the n minus first. And the second derivative will equal the power series going from n equals 2 to infinity of n times n minus 1 times cn times x to the n minus 2. So this is exactly the same as in the last problem. The power series for y, y prime, and y double prime. And what we're going to do, of course, is we're going to plug in those power series into the differential equation, which is done right here. Let me give you a moment to catch up. Okay. Please ask any questions. Okay, so now what we want to do is naturally for this step right, I mean we're right here. Of course, I want to distribute through the functions that are in front of the power series. Have to do that next. And when I do that, I'm going to get an equation with 5 power series in it. 5 power series in it. Okay. Now, naturally, to combine the power series, we focus on the exponents in each power series, the term with the exponent in it. And based on that, that determines how we assign the indexes. So the first power series will let k equals n minus 1. The second power series will let k equals n minus 2. Third power series, k equals n minus 1. You know, we want x to the kth power, right? That's why we're, you know, assigning as appropriate. Fourth power series k equals n, and the last power series is k equals n also. Okay, and all right, let me know when you're ready to move to the next page. I know you're writing things down in your notes, but see, if I were in the classroom, I could kind of look and see, you know, but I can't do that remotely so easily, you know. All right, Matthew, very good. Okay, Paige. Okay, Andrea. Thank you.
I am also good.
Justin's good. All right, very good. Okay, Cathea's good. Antonio's good. Thank you. So this is a little like the, you know, the Nike ads. Nothing, just do it, right? That's what we're doing. Okay. We're going to combine these 5 power series. All right. Paige, you're good. Excellent. Okay. So we move to the next page. Now, of course, we have rewritten our power series all in terms of the K index. Now it turns out that the highest index is K equals 1. Okay, K equals 1. So that is the index that like rules. Okay. So what I'm going to do here is take the remaining. Let me just make sure here. One moment. Well, there are 2 power series that have K equals 1 index, 2. So that means there are 3 power series here that I have to separate out a little bit. Meaning that, like for the first power series, I'm gonna write out the first term plus then the remaining of the power series starting at K equals 1. So this matches with this. Okay, for example. And then the second power series, I write out the first term. And so that power series matches with this power series. And then obviously the last power series, I write out, oh, hold on here, one moment here. Yeah, that's right. And then the last power series is written out here, the first term plus the remaining power series. And by doing that then, let's see here. Well, I'm going to have a 2C2 here. I'm going to have a minus 2C1 here. And then I have a C sub 0 here. And I can combine then, let's see, the other 5 power series together. I can combine the remaining 5 power series. They all start right at k equals 1. At k equals 1, and I can combine those 5 power series and write the power series. When I combine those 5 power series, I can combine them into one power series, whose term consists of the sum of every term. It consists of the sum of the terms in the power series, which is what we have here. Let's see, do I have 5? 1, 2, 3, 4, 5. Yep. It's absolutely amazing. It really is amazing. So these 5 coefficients here, I'm going to combine the 5 coefficients, and that will give me then this coefficient for every x sub k term in the power series. K plus 2 times k plus 1 times c sub k plus 2 plus the quantity k plus 1 times k minus 2 times k plus 1 times c sub k plus 1, then finally plus k plus 1 times ck. Hold on, Zachary. The middle term in pink. Hold on. Let me see here. Let me clear. Which you mean? Which are you talking here, Zachary? The very last step. Okay. You're talking right here. So maybe with your pen. Okay, go ahead, circle for me. X to the 0th power. That's x to the 0th power. Okay, and then okay, you're now at the bottom.
Everything
Okay,
in the pink is combined into this line at the bottom, right?
that's correct.
Okay.
That's correct. So, yeah, let me show here. Hold on here. So here's the pink. And you can combine that together to get this expression here that I'm circling in red.
Okay, I have another question. So then, is this expression right here in the middle? is this thing goes into this thing right here, or no?
It does. It does. It does. In other words,
Okay.
k plus 1 times k minus 2 times k plus 1, it can be written as k squared plus k squared minus 1k minus 2. And that can be factored then as k plus 1 times k minus 2. And also, the way I got that whole thing is the k plus 1 times ck plus 1 term and the minus 2 times k plus 1 times ck plus 1 term. I brought those together, k plus 1 times k plus 1 times k, minus 2 times k plus 1. That's how I got this here. Simplification of terms. That's exactly right. There's no division. There's no division. There's no division. This means here it's a bracket. It means like if you go 3 times 2, 3 times 2, that equals 6. That's what I mean by this bracket here. It's a bracket. Good question. It's a bracket. It's not division. It's just a bracket. Zachary, you're okay? Okay, excellent, excellent. And on my notes, I'm making that bracket a little more. All right, are we ready to move to the next page then? Okay. There's the bracket. Okay. Okay, so then here's what we have. So before I started to enumerate out what my coefficients are going to be, I wanted to simplify what was inside the term for the power series, the terms. And so now we do the same thing we did for other example. Okay, the 2c2 minus c1 plus c0 would have to equal 0. And the coefficients in the power series, okay, the coefficients in the power series also have to all equal 0. There's a k plus 1 here.
Wait, is this top thing, is this just a rewriting of something on the last page?
It is. It's just a rewriting. This here, it should be, it's k plus 1. This is just k plus 1, right?
Wait, actually, can you just go back to the last page for a second? I'm sorry.
Sure.
Okay, I'm good, thank you.
Okay. K plus 1 there, good. So we have then these two relationships. And notice this time for the iterative formula, recursion formula, it starts at k equals 1. Why does it start at k equals 1? The last time, the iterative formula for the first example started at k equals 2. Well, look at the power series. The power series here starts at k equals 1. Okay, so what we do is then C2 would have to equal C1 minus 1/2 C naught. And we'll pick C1 and C sub 0. C2 is C1 minus 1/2 C sub 0. We'll pick C1 and C sub 0 to get the ball rolling. Okay. And C sub k plus 2, C sub k plus 2 here. Try to make that look good. Okay, C sub k plus 2 then turns out would equal this formula here.
Is that a -1 in that second term of the form? Yeah, to the right.
That is a negative. That is a negative.
But
yes.
Is that a 1? Is that a 1?
That is a 1.
Okay.
That is a 1. One over k plus 2. Okay. So, okay, what are we going to do now? What are we going to do? We're going to do the same thing we did last time. We're going to let C sub 0 equals 1 and C sub 1 equals 0. And by doing that, we can solve for C2. C2 would equal -1/2. And then, you know, again, for this formula, what's the first, what constants, what coefficients is it going to give for us? Well, if k starts at 1, k plus c sub k plus 2 would start then, it'll give us values. The formula will give us values for C3, C4, C5, and so forth. And so if you work it out, you're going to get C2 equals -1/2. C3 will equal -1/6. Okay. This here is a third. Okay. C4 will equal 1/8. And I just go out, you know, I just go out enough so to get enough coefficients so that I can pick the right answer and web assign. And this will be enough. Are there any questions?
Professor, does WebAssign give the like options in terms of the coefficients, or it gives in terms of maybe the sum of the n terms of that's in terms of the sigma
It
notation?
doesn't give it gives like, it's a multiple choice and one of the answers will be right. So you're not going to type in the answer, at least for most of them, you'll be selecting an answer, Michael. You'll be selecting the right answer. So you want to be careful, right? You want to be careful because if there are 5 choices, you have 2 tries. So you want to be careful.
So
sometimes
what
the
I'm
solutions,
asking is,
sometimes they look very similar, the power series. So you have to be careful.
Yeah, what I'm
Okay,
asking is, do they give it in terms of the sigma notation, or they give you the write the sum out and
they
give the
write the sums out.
coefficients?
They
Okay.
usually write the sums out. Yes, that's right. The reason they do that is because the sums, sometimes when the sum's written out, you can figure out like what function the sum goes with. Like for instance, e to the x. It wouldn't be hard looking at a power series to see if that were equal to e to the x. But the other power series, it's harder to figure out the functions for those. And so they just write out the terms of the series. But I hear what you're saying. And then also, well, I'll mention also the power series, if so they're happy if you get the right power series. But then writing the power series or figuring out the formula for the power series is an extra step that they're not worried about for the most part. All right, good question. Well, let's move to the next page if we're good. Are there any other good questions? Okay, well, now with c sub 0 equal to 0 and c sub 1 equal to 1, okay, for that, you'll solve the coefficients as well. Okay. Let me make this a little darker. This is 2 plus 2 here. C2. This is C1. And so you get the second power series then. Well, you get some terms of the power series. And so the general solution would be here. And these coefficients, the big C1 and the big C2, those are not the coefficients anything to do with the power series. Those are separate coefficients. So in WebAssign, so like Michael, this would be like one of the choices in WebAssign. Well, what WebAssign would do, what WebAssign, I think, if I recall, does is it'll say Y1 equals that power series, and Y2 equals that power series. It'll give that as a choice. But then it'll give it'll give Y1 equals another power. It'll give different choices for Y1 and Y2. No, Zachary, there's no C3 here. There's no C3. This is just like what you like. Think about the two power series form a fundamental set of solutions for this second order differential equation. The differential equation is going to be, the general solution is a linear combination of two functions, or equivalently a linear combination of two power series. That's the general solution to the differential equation. That's all you're doing. You're just writing out the general solution in terms of not functions now, but power series.
Professor?
All right, good question, Zachary. Yes, Antonio?
Is it just a coincidence that the terms alternate between terms like 1 and 0 and constant and 0, like, because in C1 you have all of the odds are actual numbers, and in the second one all the evens are numbers? So like if you
there is, it has to do with, there are functions that represent those power series. So there is a reason for it, but there's no I can't say there's a general I could have predicted it. Let's put it that way. When I worked this problem out, I could not have predicted it. You just have to work it out and you know, kind of see what happens, basically.
Yeah, I just meant like, is there a way to combine them to where they make one summation, like one power series?
Well, you don't want to combine them. You don't want to combine the two power series. You want to keep them separate because the general solution to the differential equation is a linear combination of two solutions. Both solutions together make up your fundamental set of solutions.
Okay.
So you want to keep it separate. You don't want to bring them together.
Okay.
Good
So
question.
depending on what your C sub 0 and C sub 1 are, you'll get different constants, but the same power series.
Well, you know, the power series here, they're different, the two power series. I mean, this power series here has a 1, has an x term. Power series above doesn't have an x term, has a 0x. That's different enough for me. But a good question. So now, class, we also in this problem have an initial condition. So let me show you how to deal with that. And I might just have to kind of, you know, go forward here, and I don't know if you have time to copy. I'll probably just let you copy if you want. But what you do is you let y of 0 equals 2, and then you substitute in, like the first power series, if you let x equals 0 in the first power series, you're going to get a 1. And in the second power series, if you let x equals 0, if you substitute it in the second power series, you're going to get a 0. Okay, and so 2 will equal C1. C1 is 2. And so what you do is you put 2 back into the power series for that's what big C1 is. It equals 2. You put it back in the power series, okay, and then you do a little, you know, simplification, and now you take the derivative of y here. You take the derivative of y. This is y. Very good questions, you know. I like answering questions very much. You take the derivative of y, and now, you know, you're taking the derivative of polynomials. When you take the derivative of polynomials, you're going to get, you know, you're going to get a very nice expression. Okay, so like the derivative of 2 minus x squared minus third x cubed plus a fourth x fourth is negative 2x minus x squared plus x cubed. The derivative of x plus x squared minus a fourth x to the fourth is going to be 1 plus 2x minus x cubed. And now that you have the derivative of your general solution, now you can solve for C2 by putting in 0, letting x equal 0. Okay, and if you do that, y prime of 0 will equal negative 1, which will equal 0 plus C2 times 1. Hence, C2 is negative 1. All right, so, and then I'll give you a moment to copy that, and then we'll go to the next page. I know if you can stay a few minutes, great. If you can't, it'll be on the recording. I understand. I understand. But if you can stay a few extra minutes, it's always appreciated. It's not like you have to hop in your car, right? Or to get on the bus, right? Right. Okay, Matthew, very good. We just got one more page to go, very easy. We know that C2 equals negative 1, so we're going to put that in here. Good, Antonio. Does anybody else need another moment or two to copy this page? Okay. All right, so I put in then C1 equals, well, I put in C2 equals -1. There it is, right
Is this
here.
the last page?
This is the last
Okay.
page. And then, you know, I just expand it out, combine some like terms, you know, and then this is the solution to the initial value problem. And no matter what, like for getting the power series solutions, no matter what C's that you were to use, if you were to let, like I let C sub 0 equals 1, C sub 1 equals 0, and C sub 1 equals 0, C sub 1 equals 1, you know, and that's what you want to do. You want to do that. It's easiest, and it'll help you. You'll get the WebAssign answers, you know, that they want. But no matter what, like your power, no matter what coefficients, no matter what the coefficient values are, depending on what you assign for your starting C coefficients, your C values, you would get this answer no matter what, because the initial value problem only has one unique solution, right? And on that note, that's basically it for this example. Now, the only thing I'll mention is in the homework for section 6.2, the second batch of exercises due on Tuesday, there is a problem where you have a second order differential equation where one of the functions in front of the y is a cosine of x. Okay, so look at example 8 for that. Example 8 in section 6.2. You want to look at that example because I want to say it right. I maybe didn't say it right. In example 8, one of the functions in front of the function in front of the y is a cosine of x. You haven't seen a cosine of x function in front of y. You've seen, you know, like polynomial functions, you know. So you want to look at example 8 in section 6.2, and that will then help guide you for doing the very last question in the second batch of section 6.2 exercises. Okay, those will be due next Tuesday. You have some 6.2 exercises due on Sunday and some due on Tuesday. Okay, and I tried to make it reasonable because I know these problems take time. All right, thank you everybody. Thank you for a good class here. Let me stop the recording.